Okay, this is going to be our third video on sources of magnetic field. In this video we're going to be covering everything from section 28.3 of the text. Basically this is going to amount to doing one medium length calculation and then one example. We don't have too much to talk about aside from the calculation that we're going to do and then an example down here. Okay, so let's start going through this. We're going to want to calculate the magnetic field of a straight current carrying conductor. Okay, so very long wire is the kind of idea here. We have a sort of drawing of the wire here. The wire runs in the j hat direction here, along the y-axis. It's going to run from y equals minus a to y equals a, and we're interested in the magnetic field at some point P on our x-axis, a distance x from this wire. And so this calculation is going to go very similarly to the way that we did our electric field calculations back in chapters 21 and a little bit of 22, when we were looking at the electric field outside of a wire or outside of different things, right? So here we're going to do a similar thing. We're going to have an integral that we want to do, and we can kind of get started. Okay, so note that that we have this angle phi in here. We're not really going to make much use of the angle phi, but we're told that this is our angle phi, and we're also told that well, this would be the sort of complementary angle pi minus phi. Okay, and so let's take a look at how we're going to go about doing this. We're going to start off with one of the versions of the Biot-Savart law, which we saw in the last video, so I'm just going to write it out here. So this is the infinitesimal contribution to our magnetic field at some distance r is going to be given by this expression here, mu naught, our magnetic constant, over 4 pi times I dl crossed into r hat over r squared. Okay. And so very much like we did in the case of the electric field, we're going to find it more useful to write this out with not r hat here, but with actually r vector, because we're going to make use of our full vector expression for r, and we don't want to have to extract the unit vector from that. So we know that we can just rewrite this as mu naught 4 pi I dl cross r vector over r now to the third, right? And again, this is because we know that r hat is simply equal to r vector over r, right? So we just replaced, oops, there should be a hat. So we just replaced our r hat with an r vector on the top and an extra r in the basement, okay? And so we're going to make use of this. We're going to want to integrate this expression from minus a to a here. So we're going to see how we do that. We have to make a few modifications before we can do that. First thing we need to do is we need to rewrite our vector r in terms of x and y, because we're going to want to integrate along y, and we know what the distance x is. That's a fixed distance, and so we can kind of rewrite our r vector. So our r vector, we can see just by looking at the diagram here, well, x is not changing, right? And so our x is always going to be in the positive I hat direction, right? And so we're going to have an r vector that goes like x I hat. And now if we think about y, let's say this is our y coordinate here. If we have a positive y, our vector is going to point in the negative j hat direction. It's going to need to point negative y j hat to get here. But if we have a negative y, well, a negative y will give us a positive j hat, and that's also what we want, right? So I'm going to write it out here. If this step doesn't make a lot of sense to you right now, just give it a second and think about it, and you're going to see that for whatever your y input is, you need a minus sign to get the j hat direction out of it, so that if you add x and y, like x in the I hat direction and y in the j hat direction, you're going to get back the vector that's going to kind of run from negative a to a, right? This is basically going to be a vector that's going to change like this as it as our integral goes across and picks up all of the contributions from the whole wire, right? So let me erase that to not make a mess. And so this is the r vector that we want. Okay, we're going to be integrating over this dl, but what is dl? dl is really dy j hat, right? We have our dl segments, and our I is pointing upwards. So we really want our j pointing upwards. So it's actually a j, not a minus j. I'm just going to pause this to cough for a second. Okay, sorry about that. So yeah, so our dl as a vector is going to end up being dy in the j hat direction, right? So we want tiny infinitesimal contributions, and we really want our contributions to be in the positive j hat direction because our current is in the positive j hat direction. Okay, and so what does this kind of mean? Well, this means that our cross product, our cross product dl cross r, which we have up here, is really going to end up being dy x j hat cross I hat. That's the sort of first term of crossing these two. Then we're going to have a minus dy y j excuse me, j hat cross j hat. Okay, and so we can kind of get rid of the cross product at this point. We can do this cross product j hat cross I hat. Well, that's going to be negative k hat. Okay, and j hat cross j hat, that's going to give us 0. Okay, so the whole cross product is going to sort of simplify down, and we're going to end up with an x dy from this term here in the minus k hat direction. Okay, and so we can already do a sort of little double check as we're going here. We can see that they've supplied for us the direction of the magnetic field at this point, right? And let's think about what our coordinate system would be labeled like. They gave us our x and our y, but they didn't give us a z direction here. But if this is a right-handed coordinate system, that means that our x and our y have to, if we cross x and y, like if we cross I hat and j hat, it has to give us k hat, right? And so our z coordinate would be pointing out of the page like this. Okay, so that's our z coordinate, that's our k hat direction. So we have a right-handed coordinate system, and if we then follow the right-hand rule for our current running up this wire, if we place our thumb in the direction of the current and we wrap our fingers around in the direction that the magnetic field is going to be sort of rotating around this wire, well, it actually is into the page. So it's a good thing that this thing is pointing down and away from us, and that our result is giving us a negative k hat direction for our magnetic field. This is assuming everything else will be positive, which it will work out to be. But so we already seem to be heading in the right direction, right? We have our magnetic field heading in the negative k hat direction, which is into the page. Our positive k hat direction is out of the page, and everything checks out. Okay. Before we get into sort of integrating this expression here, we also need to know what r is in terms of x and y. Well, we can kind of easily get that if we just look at the diagram. Actually, they gave it to us here, but we could easily get this just from Pythagoras, right? X squared plus y squared is going to be our third side. Well, the square root of x squared plus y squared is going to give us the length of our third side, and that is r. Okay, so I'm just going to make a note here that r is equal to square root x squared plus y squared. Okay, and this means that since we want r cubed, this is going to mean that r cubed is equal to x squared plus y squared all to the 3 over 2. Okay, and so I'm going to take a second here to rewrite our dB, our infinitesimal contribution to the magnetic field at that point. Let's rewrite it. We're going to have dB is now equal to, well, we still have these leading coefficients here, mu naught over 4 pi. We still have our I, but now we have, instead of this cross product, we have x dy in the negative k hat direction. Okay, and then instead of r cubed, we have our x squared plus y squared to the 3 over 2. Okay, and So now we're going to want to integrate this thing, okay? And let me see how much space I have here. Oh yeah, we got lots of space. Okay, so what we want is the full magnetic field at that point, right? To do that, we need to integrate over all the little contributions, all these little dBs, over the full range that is contributing to dB. Well, we can rewrite that in the form that we have here, right? So I'm going to factor out everything that isn't going to be hit by the integral. We're integrating in dy, so only terms that go like y need to stay in there. We're going to end up with mu naught I. We have an x upstairs that I can pull out. We have a 4 pi in the basement, and we still have this negative k hat that can be pulled out also. Then we have the integral that we need to look at. We're going to be integrating from negative a to a, and it's going to be dy x squared plus y squared to the 3 over 2. But we've already seen this integral a number of times, right? And I've even gone to the trouble of putting it into our formula sheet. So we can go through and do the trig substitution to re-get this integral. And if you guys don't remember how to do that, I would suggest that you go back and take a look at our work in calculating the electric field outside of different shaped things, right? But for now, we can just look it up in the formula sheet. In the formula sheet, we see that we have the indefinite integral dy over x squared plus y squared to the 3 over 2, and we know that this gives us y over x squared square root x squared plus y squared. Okay, so we know this indefinite integral from our formula sheet and from our previous work. So we can just take this result and evaluate it at minus a and a to get ourselves an answer here. Okay, so we won't even have to do the hard work of integrating. We'll just sort of skip that. Maybe I'll write it one more time on this page and then move on to the next page. So basically what this amounts to is that our magnetic field is now going to be mu naught I. We're going to cancel, so we're going to end up with an x squared in the basement here, but we already have an x up here, so I'm just going to have a 1x in the basement, right? So we're going to have 4 pi x, right? Getting rid of this x and getting rid of this x squared from the bottom. And we still have this minus k hat sitting over here, and now we need to take our result, which is y over square root x squared plus y squared, and remember we don't have that x because we just dealt with it, evaluated at a and minus a. Okay, evaluating that square bracketed factor from a to minus a is going to end up giving us, well, maybe I'll rewrite it fully here. So we're going to have b equals mu naught I 4 pi x minus k hat, and then we're going to have, evaluating at a, we're going to have a over square root x squared plus a squared, okay, and then minus a over square root x squared, and minus a squared is just going to give us a squared. Okay, so we can clean this up. This is going to end up giving us, maybe I'll rewrite it all again. This is going to give us mu naught I 4 pi x minus k hat, and we're going to have a factor of 2a square root x squared plus a squared over here. Okay, so this is good. This is sort of what we're looking for here. But let's clean this up a little bit, because what we're really interested in is the magnetic field outside of a very long wire. So this is our result. Maybe I should put a box around this. This is our result for a wire that extends from negative a to a. But let's say a and negative a, or let's just say that the magnitude of a is much larger than x, right? So let's say we're looking at a very long wire, an infinite wire, or we're very up close to a pretty long wire, right? In that case, oh, and I am running out of room here. Okay, so in that case, let's take a look at this final factor here. We can rewrite 2a over over square root x squared plus a squared as, and I'm going to kind of bunch it up on one line here to save some space, 2a over, let's say, square root. I'm going to factor out an a squared, and so we're going to have x squared over a squared plus 1, right? I can factor out an a from this stuff down here, and it gives me that. Well, I can pull the a outside of the square root, right? And it'll just become an a, because the square root will hit the square, and so it'll just be an a, so these will cancel, okay? And I can rearrange this to give myself 2 over square root 1 plus x squared over a squared, right? But then for, and maybe I'll write it here, for a much, much greater than x squared, well, okay, implies x squared over a squared goes to 0. Okay, so if a is huge and x is tiny, well, a squared in the basement with an x squared on top is basically 0. And so this means that our 2 over square root 1 plus x squared over a squared basically goes to 2 over square root 1, which is basically, well, which is 2, right? And so in that case, we can replace this whole right-hand side last factor here with just the number 2, and if we do that, we're going to see that we have for long wire, we get a b that looks like mu naught I over, and now since we have a 2 upstairs, basically all this is turning into just a 2. It's going to kill off 2 of the 4 in the basement, so we're going to end up with 2 pi x, and this is going to be in the minus k hat direction. Okay, and this what we have written here is basically the result that they come up with in the text. They call this r. And so x and r are the same thing here. They're just the distance from the wire that we're taking the measurement, right? So x is because we were in the x direction. R is a sort of radial coordinate, so you can think of it anywhere around this infinitely long wire, a distance r from it. Okay. So 28.9 here. This result is definitely something that we're going to want to keep at our fingertips. Okay. I won't box this one, but we'll have this one boxed, which is for a wire of length 2a, and we have this one, which is for an infinite wire. Okay. When we're dealing with this wire, the right-hand rule still applies. We can kind of see a little drawing of it here. We have the wire with current going from left to right here. We line our right hand up with it such that our thumb is pointing in the direction of the current, and our fingers curl in the direction of the magnetic field, right? So we still have that useful tool. Okay, so now we're going to take this result that we have here, this result for the magnitude of the magnetic field, right? And we're going to use it over here. So maybe I should note really quickly this result for k hat and x. Well, this k hat part of it is only going to hold if our x really is in the x direction and our current runs in the positive y direction and so forth. This strips off that directional information, but the magnitude is going to be true no matter how we orient the wire, right? So we can use this result and then not have to recalculate everything, but use the right-hand rule and just sort of reason out which direction this thing is going to have to point in, and we know that the magnitude will always be given by this expression here. So that's what we're going to do in this next example here. And so this is an example where we are looking at the magnetic field around 2 very, very long wires. Okay, so let's take a look at the diagram first. We have wire 1 here. We have the current running upward and toward us, like out of the page, and wire 2 over here, the current runs downward into the page. Okay, we have our x-axis running through both wires, and we're asked about points P1, P2, and P3, which are distances some multiple of d away from each of these wires. We want to calculate the magnitude and direction of the magnetic field at all those points, right? And so in diagram B here, we can see the way that the magnetic field is kind of going to look for some of these. We can see that if we use our right hand rule here, if we look at the wire on the left, we can push the thumb of our right hand sort of into the page. Oops, no, sorry, the other direction. So the thumb of our right hand is going to be pointing upward from the page, and our fingers are going to curl in the direction of those magnetic field lines that we see there, so around the wire, kind of like counterclockwise. And then if we look at the right hand side where the current is going into the page, we can drive our thumb into that, and then our fingers are going to curl clockwise in the same direction that we see it sort of indicated here, right? So in part A, we want to find the magnetic field B at points P1, P2, and P3. And then in part B, we want to find an expression for the magnetic field at any point on the x-axis to the right of wire 2. Okay, so off over here. Let's get started and see if we can calculate those. So in part A, and let's remember, we're going to be using, maybe I'll get rid of this, we're going to be using this expression for the magnitude of the magnetic field from above. It's the magnitude of the magnetic field outside of an infinite wire. Okay, and so in part A, let's say we're looking for the, and I don't think I'm going to be able to keep this, or maybe I will. Let's put it like that. Yeah, so we can keep it on the page, and so if we're looking at P1, we're going to have a total magnetic field BT, which I'm abbreviating this B total as just BT, is going to be equal to B1 plus B2. Okay, but what are R1, our distance of this point from wire 1, and R2, our distance of this point from wire 2, right? So R1, our distance from wire 1 at that point is going to be, well, it's going to be 3D minus 2D, or minus 1D, sorry. So it's going to be 2D. We have a distance of 2D between these, okay? So let's get rid of that. And we know that R1 is going to be 2D, and R2, our distance from wire 2, is going to be 3D plus an additional D. That's going to be 4D. So R2 equals 4D. Okay? And then we can also write our magnetic field vectors B1 and B2 in terms of their magnitudes. So B1 and B2 times the sort of directional information times the unit vector in which they sort of point, right? So for our B1, how is our B1 going to point? Well, the diagram kind of gives it away here, but we can see that, again, if we use the right hand rule with our thumb pointing upward, our fingers are going to curl down in the direction of B1, and B2 will point in this direction, right? So we're going to end up with a minus j hat for B1, it's pointing downward here, and B2 will be pointing upward in the j hat direction, okay? And so with all this information, we can now just rewrite this expression. We're going to rewrite it using this over here. So what we're going to end up with is BT is equal to, well, B1 first. So what is B1? B1 is M0 or M naught, and not M, mu naught I times or over 2 pi, and it's going to be, our R is now going to be 2D, okay? Okay, and this is going to point in which direction? Well, we can see it from our expression over here. It's going to point in the minus j hat direction, okay? And what about our B2? Well, our B2 is going to be mu naught I over 2 pi times 4D, right? Because our R2 is 4D. So we substitute in our 4D, and what direction does this point in? Well, it points in the j hat direction. Okay, and so now we can just add these up. I'll do that here. We're going to end up with mu naught I over 2 pi d. I'm going to pull out a j hat here, and then we're going to have minus 1/2. That's what remains here after we pull out this leading factor, plus 1/4 here, right? And so what does this end up giving us? This ends up giving us a B total, which is going to be equal to, well, we're going to have a negative 1/2 plus a quarter. Excuse me. Sorry. And so we're going to end up with an overall minus sign, right? So it's going to be like 2/4 minus 1/4. So we're going to end up with negative 1/4. And so we're going to have a mu naught I over 8 pi d, but now with a minus j hat. And I'm going to package this minus sign up with a j hat so that we end up with a sort of nice information about the direction separated out, right? So we can see that our b total over here does point downward in the negative j hat direction with this magnitude, okay? So that's the answer for point P1. I'm unfortunately going to have to scroll down, so we're not going to see the diagram anymore, but at point P2, we're looking at it here, where it's halfway between wire 1 and wire 2, so the distances, when we're looking at this, R1 and R2 will both be D, right? And they're both going to point in the j hat direction because, well, again, just straight from the right-hand rule, if our thumb is pointing upward over here, our fingers are going to curl upward, and if our thumb points downward over here, again, our fingers curl upward over here, okay? We can try that out if that doesn't really sort of right away make sense, but you can do it with your right hand and see how that all works out. So I'm going to scroll down and write down all that stuff, and then we'll work with it. So B2 is going to mean, again, that BT is going to be equal to B1 plus B2. Our R1 is going to be equal to R2 is equal to D, right? Like we said, the distance is D for both. Our B1 is going to be equal to the magnitude of B1 in the j hat direction, and our B2 is also going to be equal to, well, it's going to be equal to B2 magnitude, but also in the j hat direction. Okay, and so we can just rewrite this out as we did the previous one. BT, now substituting in for B1 and B2, is going to give us a mu naught I over 2 pi d in the j hat direction, and B2 will give us the same thing. It's going to end up being mu naught I 2 pi d in the j hat direction. So we just end up with a factor of 2 on the top, which will cancel the factor of 2 on the bottom, giving us a mu naught I over pi d in the j hat direction. Okay, that's our BT for point 2. Let's just quickly take a look at that. So it points in the j hat direction, and it has a magnitude much larger than that of our first one. Does this all make sense? Well, it makes sense that it points in the j hat direction for sure, because both components point in the j hat direction, and the magnitude is much larger because this is the point at which both wires are contributing as much as they possibly can, and still being equal, kind of, right? So they're both contributing equally, and it's as close as it can get to both of them, sort of, right? So that's point P2. Let's take a look at point P3 now. What do we have going on at P3? Again, if we follow the right-hand rule, our B1 contribution is going to be pointing in the j hat direction, right? If we think about our right-hand rule on wire 1. And our B2 contribution is going to be pointing in the negative j hat direction by thinking of the right-hand rule on wire 2, okay? And the distances are going to be, it's going to be a distance of 3d from wire 1 and a distance of d from wire 2. Okay, so let's write all that out and then get to solving here. I'm going to do this on the next page. So C, or no, not C. This is just more of part A, but now this is going to be for P3. So P3, again, we can rewrite it like this, and this should be T, not a plus. It's going to be equal to B1 plus B2, with R1 equal to 3D and R2 equal to D. And we can rewrite our B1 vector as the magnitude B1 in the j hat direction, and our B2 we can rewrite as magnitude B2 in the negative j hat direction, okay? And that's all the information that we sort of reasoned out by looking at the diagram. Now it's just a matter of simple substitution, so our BT is going to be equal to mu naught I over 2 pi 3d, right, like that. This is going to be in the j hat direction, and our second term is going to be mu naught I over 2 pi d in the negative j hat direction. Okay, and so we can add these up, right? So we're going to end up, I can factor out the sort of leading terms here. We're going to end up with a mu naught I over 2 pi d in the j hat, and we're going to end up with a 1/3 minus 1 here. Okay, 1/3 minus 1 is going to give us negative 2/3, and we can cancel out this 2 with this 2. And if we rewrite this, we're going to end up with a b total equal to mu naught I over 3 pi d in the negative j hat direction. Okay, and so that's the answer for the magnitude and direction of the magnetic field at P3. Okay, and now the part B, the last part of the question here, wants us to write down an expression for the magnetic field at any point to the right of wire 2. Okay, well, we can do that pretty simply because we can see what R1, our distance, is going to be in terms of d and x, and what R2 will be when we're to the right of this wire, right? So when we're to the right of wire 2, our R1, our distance from wire 1, is always going to be x plus d, right? It's always going to be the x coordinate plus whatever this extra d was here, right? And for R2, it's just going to be x minus d, right? Because this is our origin of our x coordinates, right? So let's write those down. This is part B. For part B, we're going to have R1 is equal, and that looks not good. R1 is going to be equal to d plus x, or I guess I'll write it like this: x plus d, and R2 is going to be equal to x minus d. Okay. And so what is the direction of our B going to be? Let's take a look at that. Our B1, we know we can write it as B1 times some direction, and our B2, we can rewrite that as B2 times some direction. What are those directions going to be? Well, the right-hand rule is going to guide us here. For wire 1, if we use the right-hand rule, our excuse me, our B1 is always going to point upward, so that's always going to be in the j hat direction, and our B2 is always going to point downward, right? Both from the right-hand rule. So we can write this as B1 j hat and B2 minus j hat. Okay. And then again, it's just a matter of simple substitution. So we'll write down B total for any point out there. I mean, I guess we could write this like B total as a function of x is going to be equal to our contributions B1 as a function of x plus B2 as a function of x, right? And this is just going to be equal to mu naught I 2 pi. Now we replace the r with x plus d, right? Because we're dealing with the first term here, so this is going to be x plus d. This is in the j hat direction, and I'm going to just factor out that minus sign, so we're going to have a minus mu naught I 2 pi x minus d in the j hat direction. Okay, we can clean this up a little bit. I'm going to move our mu naught I over 2 pi and our j hat over here, and then we're going to have a 1 over x plus d minus 1 over x minus d. I'm going to multiply each of these by, well, I'm going to cross multiply these basically, so we're going to end up with a mu naught I 2 pi j hat, and so we're going to have an x minus d minus x plus d over, and now we're going to have the product of the two denominators in the basement here. We're going to have x plus d times x minus d. Okay, and this is going to clean it up a little bit. So we're going to end up with, we're going to have, well, these x's are going to go away, and we're going to have minus 2d on top, so we're going to have mu naught I 2 pi j hat minus 2d on top, and in the bottom we'll have x squared, cross terms go away, minus d squared. Okay, a little more cleaning, we can get rid of these 2's. I'll pull the minus sign into the j just so that we have sort of our direction set up for us, and then we're going to have a b total, which is going to be equal to mu naught I, still have a d upstairs, and then a pi x squared minus d squared in the basement minus j hat. Okay, and that is an expression. I guess I can write this like this. So b as a function of x is going to give us that expression for the magnetic field at any point to the right of our second wire. Okay. So that was sort of the derivation of the magnetic field outside of a wire of length 2a, and then we built that into a definition for the magnetic field outside of an infinite wire, and then we used that result in an example here. It's going to be useful, or it's going to be important to know how to derive that expression for the magnetic field outside of a wire. You may be asked to do that for a different point on a maybe not infinite wire or something in either one of these term tests or on the final. So make sure you understand the sort of derivation of that, and make sure you can also use the result as we did in this final example here. Okay, I'll leave it there for now, and I'll see you guys in the next one.